Okay, good morning. So we've learned a little bit about sound, some concepts, some ideas. I threw a couple formulas at you, and I'd like to show you how to use some of those today. We still have two more things new to learn from this chapter, and that is we need to learn about resonance. We also need to learn about the harmonic series, which is the secret to music. But thunder and lightning, this is an example of something that I think is very entertaining because most students get surprised when they find out that their parents have lied to them. So both light and sound are wave phenomenon, meaning that they travel at a specific speed. The speed of light gets the letter c, and it happens to be 3 times 10 to the 8 meters per second, or 300 million meters per second. But sound is substantially slower at 343 meters per second at average room temperature. Okay, so what happens if we have a lightning strike over here, and this is your lightning strike picture, and you are over here, and let's make these guys separated by 1 mile, which is 1,609 meters. Is that a number you should remember? Oh, heck yeah. If you remember that there's 1.6 kilometers or 1,600 meters in a mile, you'll be able to go back and forth in the metric system between distances that you might walk or be asked to run. Anyway, at this point, what's going to happen is two things. First of all, there's going to be a flash of light. I'll draw it like this, and that's going to go towards you. And then there's going to be some sound, and I'll draw that as this, and that's going to go towards you. Now, we can figure out how long it's going to take for you to hear this stuff by using the basic, uh, you know, relationship, the distance equals speed times time. Now, in the case of the light, that means that the distance is going to equal the speed of light times time, or that the time is going to be the distance traveled divided by the speed of light. So 1,609 meters divided by 3 times 10 to the 8 meters per second. And I'll get my handy dandy calculator out here, and let's do this. 1609 divided by 3 EE8 equals, and that's going to be about 5.4 times 10 to the minus 6 seconds, or about 5 microseconds. Okay, so within 5 microseconds of lightning striking a mile away from you, you will see the flash. Now, the interesting thing about this is that is when you start counting. So the amount of time that it's going to take for the speed of sound, that sound wave to get to you, is going to be that same distance divided by the speed of sound. So that's 1,609 divided by 343. And I haven't left myself a whole lot of room, so let's move down here. And that's another thing we can do on the calculator. 1,609 divided by 343. And that's going to be about 4.7 seconds. Now, we have to subtract the 5 microseconds off of that, but as you can see, 5 microseconds will be way over here in a decimal place that we don't even represent. So essentially, we can ignore the time it takes the light to travel to you, and lightning that hits a mile away takes about 4.7 seconds for the sound to get to you. Now, the part that makes your parents into liars is that I was told, and I'm sure many of you were told, that when you see lightning, you start counting 1, 1,000, 2, 1,000, 3, 1,000, and for every second you count, the lightning was a mile away. Well, that is not true. For every 4.7, or about 5 seconds that you count, lightning was a mile away. So, that's not a small lie. That's a factor of 5. Not that you were in any more danger, and I'm sure your parents were trying to reassure you, but now you should know the truth based on the fixed speed that sound travels about 1 mile every almost 5 seconds. And that brings up an interesting point. We use waves to measure distances a lot because, let me write this out before I talk. They travel at a fixed speed. All right, so that's a very important moment, and you used an equation, distance equals speed times time. Let's put a box around this guy right here, and we prove that your parents are. Now, when you have kids, you have a choice. You can decide to continue the lie or to tell them the truth, and you'll have to make that decision based on context. Okay, next thing I want to talk about. This is a story called Why Harmon is Deaf. Ish. I have tinnitus. It's a ringing in my ears, and I got it from a lot of my habits and hobbies when I was younger. I liked live music quite a bit, and I would go to concerts, and I played music on stage, and subjected myself to a lot of really loud noises. So let me show you, using our two equations about intensity, what's going on here. Now, the first equation about intensity is that intensity is the power in the sound wave divided by 4 pi r squared. And I may not have said where that r squared comes from. That is the surface area of a sphere. So the sound is spreading out over ever larger and larger spheres as it moves away from its source. The second thing I said, and I don't believe this is in your book, is that the decibel level is 10 times the logarithm of the intensity level divided by a reference intensity, which is 10 to the minus 12 watts per meter squared. We're going to use these two equations, and we're going to use them forwards and backwards. Now, this one is not so bad to use forwards and backwards because it's strictly algebra to undo it, but this one's got a log in it. So I want to remind you that what is log? So if we wanted to undo this and get to this intensity, which is hidden inside of this thing, first of all, we could take the number of dBs and we could divide by 10. That would make it into bells, and that would be equal to log of I over 10 to the minus 12. Now, what is the opposite of log? And it turns out that it's 10 to the. So 10 to the power of the decibels divided by 10 equals I over 10 to the minus 12. And now we're back into the world of algebra where I is 10 to the minus 12 times 10 to the decibels over 10. So you can reverse this thing, but you have to know that the opposite of log is 10 to that power. That's what logs do. Okay, so let's draw a picture. Here is somebody who is playing guitar on stage. Let's put an afro on it. Let's make it Jimi Hendrix. Okay, there's an afro and a headband, and I'll draw him holding the guitar in a non-standard way. There we go. And he's standing in front of a very large amplifier or set of amplifiers. And this is back in the 60s how we used to do rock music. So the audience is over here on the ground, and they're some number of meters away, and they want to hear a nice loud guitar solo. So they would like to hear 80 decibels at least, just from the guitar. I mean, the rest of the band is going to contribute a little bit, and the whole experience might be 90 to 100 decibels. But they want to hear it really well. Now, how far away are they from the stage? Well, if you don't get the really good seats, you're a couple tens of 20 meters away. See, 20 meters is 60 feet. I'd say you're more like 100 feet, but let's go ahead and use let's use 30 meters away. Okay, so if somebody 30 meters away needs to hear 80 dB. The question is, how loud is it for the performer? Okay, and so we're going to work this out. Now, first thing we're going to do is we're going to say for the audience member, what does 80 dB correspond to? Well, according to our modified formula here, the intensity associated with 80 dB is is 10 to the minus 12 times 10 to the 80 over 10, or 10 to the minus 12 times 10 to the 8. Now, if you know anything about exponents, when you multiply the same base and exponents, you simply combine the exponents arithmetically. So we're going to be adding 10 to the minus 12 to 10 to the 8, and we're going to get 10 to the minus 4. That's how many watts per meter squared. Now, from this, we can figure out what the power is at the location of the audience member. Okay, let's do that. That's over here. That's going to be the intensity times 4 pi r squared. Now, ten to the minus 4 times 4 pi times 30 squared. The power in the wave and that's the power at the source, right? Because this thing says the intensity at your location is the power at the source divided by 4 pi r squared. And let me get my calculator out here. So we're going to do 10 okay, that's a comma. 10, the exponent minus 4 times pi times 30 squared. Okay, that's going to be 11.3 watts. There's 11.3 watts of energy coming out at the source. And now we can feed that in over here and say at the location of the amplifier, there's 11.3 watts. By the way, this is kind of funny because most of these guitar amplifiers are hundreds of watts and sometimes many hundreds of watts of electrical power necessary to make a very small amount of acoustic power, of power in sound. That's because speakers are horribly inefficient. All right, so now we can figure out what's the intensity at the performer's location. Well, that's going to be the power, 11.3 divided by 4 pi times the location of the performer squared. Now, how far is the performer from the amplifier? Let's be generous, and let's just say that this person is 2 meters, or about 6 feet away. Social distancing space. Okay, so here we go. 11.3 divided by 4 pi times 2 squared. By the way, 2 squared you can do in your head, that's 4, but let's get this cranking. 11.3 divided by 4 divided by pi and divided by 4, again, equals 0.225. So the intensity in watts per meter squared is 0.225, and you can see that's a lot more than it was out at the audience. And so let's figure out what the decibel level is for that person. That's going to be 10 times the log of 0.225 divided by 10 to the minus 12. And now, when you divide 10 to the minus 12 into something, it's like multiplying by 10 to the 12. So what I'm going to do is I'm going to multiply that answer by 10 exponent 12. And then I'm going to take the log. Okay, now I got to find the log button on this thing. Log of that answer. And then I'm going to multiply by 10. And there it is, ladies and gentlemen. The decibel level on stage is 124 decibels. So that could be above the level of pain. That is certainly going to be damaging to your hearing for long periods of time, and you would probably need to wear earplugs. If you don't, because you say, hey, I need to hear everything going on stage, you risk losing your hearing, and this is what happens to a lot of musicians. Now, this is not how music is performed anymore. For the most part, the volume level on stage does not create the volume level out in the audience. The volume level on stage is low enough so that people on stage can hear it, and sometimes the first few rows can hear it, and then it is picked up by microphones, and then it is broadcast using some speakers which sit in front of and above the performer, and that's what blasts out to the crowd. And they're up high because that way, when there's a crowd of people, then the sound can be coming down from above and get to each row. So that's a little fun thing that's going on with that. So that's one of the reasons why I am deaf. Okay, let's do one more thing here, and this one's really simple. Those of you who play rock and roll or with a bass player, you may discover that bass players don't understand how loud they really are. Or the other problem here is that bass players have trouble hearing themselves on stage without becoming too loud. And one of the biggest complaints, if you have somebody who's mixing your not stage volume, but your performance volume in a club or something, is they say, hey, we need you to turn down the bass. And then the bass player says, well, I can't hear what I'm doing. There is a scientific reason for it. Now, most of the time, people on stage put their amplifiers on the ground, and then they stand pretty much in front of them. Maybe this is not a good example because this makes it look like this amplifier is as tall as the person. We should probably draw the person being a little bit taller. Yeah, bass players are taller anyway. So there's your bass player. And what happens is the sound waves are coming out of the bass and going this way. The thing is that the sound developed by an amplifier or speaker doesn't generally reach kind of full volume and full intelligibility until it gets at least one wavelength away from the speaker. If you sit too close to it, you're not really getting the full effect. And I don't know why this is, and it might be psychosomatic, psychological. I just rub my eye, which of course you're not supposed to do, but you're especially not supposed to do it after you've been chopping jalapenos, which I was doing about half hour ago because I'm making tacos tonight. Gosh darn it, this is killing me. Ah, okay. So we need to figure out how long this wavelength is, and we're going to use our basic wave equation. Now, the speed here is going to be the speed of sound. We're solving for the wavelength, but what is the frequency of a bass note? Now, I think you remember when I drew that graph that the lowest frequency that a human being could hear was 20 hertz. Would it not surprise you to hear that some notes on a bass guitar are very close to that? Something between 20 and 40 hertz for the lowest string on a bass guitar. So let's just call it 30 hertz for this particular note. You can actually look up what note that is. In fact, 55 hertz is the A string on a bass, so this might be the E string on a bass. So let's go ahead and do this. 343 equals lambda times 30. So lambda is going to be 343 divided by 30, and that, well, you can obviously tell it's going to be about 10, is 11.4 meters. So the full wavelength of the bass guitar doesn't really go until 11.4 meters away from the amplifier. So the bass player really needs to be further from his or her amplifier in order to make this work out. Now, one thing that you can do, and I've done this in a lot of venues, is if I'm playing bass, I'll actually put my bass amp in front of me. I have a fairly small bass amp, and I'll point it towards me so that it's just for me to hear, and there's a line that goes out to the sound guy so he can put it in the main mix. Another thing that you can do, of course, is what we're all doing, and that is to use a very quiet bass amp, and then you wear these little headphones. They don't look like regular headphones like this. Usually they blend into your ear, and you wear a cord that runs down your back, and you can hear whatever you want. The nice thing about these headphones is they also, mine at least, removes 27 dB of ambient noise. And the reason why that's important is this guy. The drummer, who is making the most god-awful racket. And if you're the bass player, you're generally stuck standing next to the drummer, and you will become deafened to his or her machinations if you're not careful. Okay, so I think we showed you a couple of things. By the way, for those of you who want to look into this further, I think the real number is it's about half a wavelength is when the sound develops, and that the reason why has to do with standing waves. You'll recall that in a standing wave situation, oh God, that's so beautiful. This is a node. That means there's nothing going on. So you're before you get to the first antinode, you're over here. So maybe that's a quarter of a wavelength. I'm not sure, but anyway, the point is that when you get the standing wave situation, which you get with bass frequencies inside of a room a lot, you have to be away from the nodes to get the antinodes. Actually, no, because the fundamental actually looks like this. The antinode is now still a quarter of a wavelength. So I think that's the answer, that due to standing waves, it's a quarter of a wavelength away. All right, well, that's good enough for today. I'll hit you with some other interesting stuff tomorrow.